Hi everybody, I am Antoni Cladera from Universitat de les Illes Balears, the University of the Balearic Islands, and I'm going to present this communication entitled Shear Strengthening of Reinforced Concrete Members using Shape Memory Alloys towards a more ductile shear failure. This presentation summarizes the work carried out at our university. I would say that maybe around 5 years. And basically, the work for the PhD thesis of Joan Rius and also a little bit of Benito here, we will see, not all, and supervised by Carlos Ribas and myself. This is the exact presentation I will perform in ACI Spring Convention in Detroit, in fact, just 2 hours later. Shape memory alloys, maybe some of you are not very familiar with shape memory alloys, but shape memory alloys are a reality nowadays. You can find many research regarding shape memory alloys. For example, this active confinement using nickel titanium niobium. This was a experimental campaign reported by Shear and Andraues a few years ago, and it deals with active confinement generated using a nickel titanium niobium wire that confines and creates an active pressure, as you can see here in these columns. Okay, this is nickel titanium niobium. They use for this research, they are using shape memory effect. And also in the last issue of ACI Structural Journal, you can find this work regarding flexural strengthening using iron-based shape memory alloys. I will talk later a little bit about iron-based shape memory alloys. And comparing to this, we can also find works that use shape memory effects. The two works before, they were using superelasticity. We will talk about superelasticity, shape memory effect in few slides. And here, for example, this paper, it's published in the last issue of Engineering-ConStruct of Elsevier, and it deals about bracing systems using shape memory link to have superelasticity. This is a nickel titanium application, and also a work on nickel titanium using a spiral of superelastic nickel titanium to create very ductile shear failures, but with internal reinforcement. Okay, I have just shown you 4 works related to the use of shape memory alloys in research, but in fact, shape memory alloys can nowadays being used in the work site, because we can find in the market rivet bars. You can see these corrugated bars here. These are iron-based shape memory alloys corrugated bars, and these pictures come from a paper by Shaverdi just 1 year ago, and this is for longitudinal strengthening. And these are strips, also iron-based shape memory alloys, and these strips we are going to use them for shear strengthening. This is our research in progress. We'll talk about this also later. So, in fact, we can also already go to the market, buy iron-based shape memory alloys specifically designed for structural concrete and to apply them. Well, what are the key properties of shape memory alloys? Well, there are 3 key properties. You can see them here. This is superelasticity, shape memory effect, and the damping capacity. All of them are the result of the so-called martensite transformation. Superelasticity, you can see it here. This is in this axis here we have stress, and here we have strain. So superelasticity is the ability that some shape memory alloys have to go, you can see here, to go through large non-linear strains maybe up to 6 or 8% in most cases, in a lot of cases, and then to go back when unloaded until 0 strain. You can see here. So we can load and unload, go to 8% of strains, that's a lot, and to go back to 0 strain. You can see here all of this area here, because there is a certain hysteresis in this process, is dissipated energy. So this is going to be a very good property for recentering, for dissipating energy in earthquakes and different applications. And then we have shape memory effect. You can see here the shape memory effect. We are going to play in this case with the stress, the strain, and the temperature in this axis here. We can pre-strain sample. You can see here we can load it. If we have it in a martensite state, we can load it and then unload, and we will have some kind of, let's say, permanent, but they are not permanent, but some permanent strains. But then when we hit the material, you can see it here, and then we cool the material, we go to 0 strain. We go to the origin, to the beginning of all the process. So this way we are going to be able to pre-strain structures. How? Well, it's very easy. We have the pre-strained material, and then if the material is free, no constraint, we hit it, and we have, you can see here, the recovery of the strains. But if the material is constrained here, then we will generate stresses, and we will talk about recovery stresses. Well, the martensite transformation is, in general, just to have a very small background, a diffusionless solid-state transformation in which the atoms move in an organized manner relative to their neighbors. Neighbor atoms continue to be neighbors. We are going to compare with plasticity. Here you have plastic deformation by slip, the classical plastic deformation. You can see these atoms here, and if we load our sample and we go to, for example, in tension on a stress higher than the yielding strength, then we have plasticity. So this atom here, A, that was a neighbor of C, then jumps, and they are not going to be neighbors anymore. So we cannot recover this strain. This is plasticity. However, if we have the martensite transformation, and we have stress-induced martensite transformation by distortion, we can have these atoms here, and we apply a stress, and then small movements are going to move the different atoms, but atoms A and C, they are going to continue to be neighbors. So very small movements, but all coordinated, so you can have very important macroscopic movements and deformations, and then unloading or hitting the material, we can go back, because these two neighbors, these two atoms, they are still neighbors, and so we can go back. Well, this phase transformation takes place in a finite interval of temperatures with some hysteresis. You can see here, for example, if we are in a, let's say, 100% martensite fraction, this is not true. We are not playing between 1 and 0 in reality, but to simplify the problem, then we are in martensite, we hit the material, we cross here the austenite start temperature, and we produce the reverse transformation until austenite finish. Here, our material will be in austenite state, and then if we cool the material, we will cross the martensite start temperature, and we will produce the forward transformation. So we will go from austenite to martensite here after martensite finish. The structure in martensite, it has a lower symmetry in general, and it is produced at lower temperatures. And in austenite, we have the material normally at higher temperature and with higher symmetry. I'm not going to talk here a lot about shear strength. I'm sure that most of you know a lot about this topic. But as you know, shear failure of concrete is sudden and brittle in nature, with little or no warning, especially for concrete beams reinforced only with longitudinal tensile reinforcement. But the failure is also fragile when you have stirrups. This is very important. And this is a classic failure of the collapse of Air Force Corps Pavilion in Shelby, Ohio, that I'm sure that all of you know. So we have been working in our research group about shear strength for years, for more than 15 years. So we had a question. Okay, we always talk about the fragility of the shear failure, but is it possible to have ductile shear failures? Because I didn't say that before, but these alloys normally present very high ductility. So the first thing we did was to internally reinforce a beam. Well, a series of some beams, and we test them, some monotonically, some cyclic or semi-cycles like here. And this is work carried out by Benito for his PhD thesis. And you can see here, this is a beam with stirrups, steel stirrups here, and you can see that after the maximum load, the behavior is very fragile. It's not ductile at all. But in this beam here with the spiral, this reference beam, I repeat, it only has steel stirrups. But here we have the nickel titanium spiral, and you can see here the shear force versus deflection under point load. The deflection measured here, the load is applied here, and here we have the reactions, and you can see that we really obtain a high, very high ductile behavior in this case. Okay, this is internal, and now let's talk about external strengthening. So we wanted to go further, and we wanted to retrofit beams, so to apply external strengthening and with pre-stressing strengthening. So we decided to pre-stress using shear membrane alloys. This is going to be very practical because you can pre-stress, as you will see, without any mechanical device, just using heat. And for this experimental campaign, you use a nickel titanium niobium alloy because it presents a wide thermal hysteresis. You can see here why the thermal hysteresis is wide, because the temperatures between martensite start, here we have a small wide window until austenite start. So we are going to be able to play with our alloy here without any problem, compared to a nickel titanium alloy that has a narrow thermal hysteresis. And you can see here that here the window is very, very small. So if we try to generate recovery stresses here in this material, then we are going to produce the forward transformation. So from austenite, we will go to martensite, and the recovery stresses at the end are going to be very small or even zero. But with nickel titanium niobium, we can buy the material pre-strained, or we can pre-strain the material ourselves in the lab. This will be the path 1 and 2. And then we are going to wrap the beam for shear strengthening, or we are going to put the reinforcement just longitudinally and fix it to the beam. So we are going to constrain this strain, and then we are going to heat it and cool it. And we will have these nice recovery stresses. Here you can see this phase diagram, transformation diagram. Temperature, we heat it. This is the path number 3. Heating here. We heat it, we arrive near, or we pass a little bit the austenite finish temperature, and then when we cool, we have here some thermal contraction, so the stresses go up until these recovery stresses. And here you have our strengthening procedure. It's very simple. We just place this pseudo spiral. You don't see the link here, there are vertical links, as you can see here. And we fix it. Here we are using U-clamps. You can see it here just to fix the material. In other beams, we are anchoring it against the concrete, and then we heat it. We are heating it here with a heat gun because we are using a very small diameter. We can also heat them using by induction with electricity, or with a torch, maybe in other research, in other programs, we have seen that they use a torch with fire. So we heat it and we produce the recovery stresses. So we activate this material. Which is the value of the recovery stresses? Well, we have tested the material here. You see a sample of, I think this is 150 millimeters and a little bit more inside the clamps. And we use a thermal chamber. So we are going to heat the material up to 200 degrees. Then we are going to keep the temperature. So the temperature in all the sample is going to more or less going to rise because we have a problem with the inertia of these clamps. The thermal inertia of these clamps is very high. So after quite a lot of time, we can cool the material. And at the end of this process we have these recovery stresses around 550, 580 megapascals, MPAs. What's the problem? That when we place the wire around our beams to wrap our beams, we cannot perform a perfect procedure. And you can see here that we have an initial imperfection. So when we start heating, we have some recovery of the strain, and then after some recovery of the strain, we have we generate the stresses. At the end of the heating, you can see that the material is perfectly straight here, but at the beginning it was not straight. So we have simulated this with in our Swig machine, and you can see we have tests with different initial imperfections. We put it like this, and then we activate, we heat it, and after heating it, it's perfectly straight. Okay, so we have tried this test with different initial imperfections, and we have seen that at the end with using the heat gun and with the real imperfection that we have, more or less, we have estimated that we are more or less in the middle, and here we'll have 425 megapascals of recovery stress. We have tested more curves that they go here until zero, until only recover the strain, but not generating recovery stresses. And here you have the preliminary results with our beams. Here you have the results of 4 beams. We have tested already around 20 beams, like these ones. Here is a reference beam. The reference beam is here, this green line here. So we have this shear force. These are very small beams for sure, because this is a proof of concept experimental campaign. We wanted to be sure that the method worked. So we built 20 beams, 20 small beams, almost like specimens, and we could very easily to try different configurations. So this is the reference beam here. Then we wrap the beam with a spiral, but we did not activate it. And you have this gray line here. And also the shear force, we are not strengthening the beam without activation. But a beam exactly like this with a spiral, then we hit the spiral. We activate the material, so we generate the recovery stresses around 425 megapascals, and then look, this is the nice behavior of these beams. This is this beam here, strengthened with spiral. We don't see that, but the back side of the beam we have inclined links like this, and look, the red line, we double the strength, more or less, we double the deflection under point load, and then the behavior is not so fragile. We are not having the nice ductility we have seen with internal nickel titanium, but we are improving. So we are working towards that direction. And then this blue line is another configuration. Here we are using U shapes, okay, and also very similar results. What is our ongoing experimental campaign? Right now we are using low-cost iron-based shear memory alloys. This material present lower recovery stresses, around 350 megapascals, but higher modulus of elasticity. This is going to be very important because, okay, maybe at the beginning we will have lower recovery stresses, so lower confining stresses, but during the test we are going to generate much more stresses than in the previous situation, because with nickel titanium niobium the modulus of elasticity is quite low. Then, okay, we can generate 350 MPa's recovery stress, but we have a lower strain recovery with this problem, so we can have a problem if there are initial imperfections. We need not to recover any strain at all, but to have perfectly confined the material, perfectly restrained the strain, and then just activated it and generate recovery stresses. We need not to recover strain. And this material you see the presentation is like more or less FRP, but with a very high ductility. You can see the stress strain behavior of the material alone. We have ductility up to 40%. We are just now starting with this strengthening method, and this research is carried out by Luis Montoya, Joaquin Ruiz, and also by Carlos Ribas and myself, and we expect to have nice results in 3 months, more or less. Just to conclude, an experimental campaign focused on assessing the possibility of strengthening critical shear beams by means of a shape memory alloy with shape memory effect has been performed. The experimental results show a promising performance of the proposed technology. We are very glad with the results we are presenting. We have presented only the results of 4 beams, but we have around 20 beams like this, and all with very nice results. This research was planned as a proof of concept experimental campaign, and for sure more research is indeed needed. And the cost of nickel titanium niobium is very high, but the recent production of iron-based memory alloy materials, specifically oriented to structural concrete industry, will boost the research. We really think so, and the real application due to the reasonable cost and excellent properties. Well, just before finishing, it's very important for me to acknowledge the support of the State Research Agency of the Spanish government and also the European Regional Development Funds, because this research has been developed in these 2 projects. So thank you very much, and thanks everybody for your attention. You can write me an email here if you want to clarify any aspect of this presentation. Thank you very much.